I can.
So just for checking, can you hear me now from the YouTube channel? Okay, so
Yes, I can hear you from YouTube, but there is a latency, I think.
Okay, so now is that clear? Is that okay? Now is that okay? Can you hear me?
Oh, still the latency is persisting.
I can hear you perfectly. So the viewers that are there, can they hear me? If you can just put down a comment, then it would be great. All right, fine. Okay, so we will start within 3-4 minutes. So Srinjoy, could you just check like 1, 2, 3, and Vamshi, if you were there, can you please? So Srinjoy, could you just check your audio?
Yeah, okay, sorry, come again, please.
Yeah, so just say something. Let's see if.
Okay, hello, mic testing 1, 2, 3.
So Angana, Vamsi, can you hear Srinjoy? So if you are live. Okay, sure. So Srinjoy, you can actually start preparing the slides, and you can, so let me first yeah, so let me first introduce me to our today's research track seminar speaker. So Srinjoy, he is currently doing Ph.D. in Chennai Mathematical Institute. He's also a member of the TCG-CREST. So all in all, he will be giving a talk today in the research track seminar on the reinforcement learning. Okay, so I hope you guys enjoy his entire talk, and if you have any questions, you are very welcome to write it down and ask him after his presentation. And if Srinjoy is also open to questions whenever he is giving the presentation, then you can also ask him uh, in between his presentation.
Yeah, in between the presentation is also fine.
Okay, then let's start with today's presentation. So Srinjoy, I leave the stage to you, and thank you for joining us, all of you.
Okay, so I should start formally now, right?
Yes, Srinjoy.
Okay, so good evening, everyone. First of all, I would like to extend my sincere thanks to Mr. Shodayan Banerjee and the entire Cheenta fraternity for giving me a chance to speak at this event. I would like to take this opportunity to talk about my research interests in reinforcement learning, which is often abbreviated as RL. So I have tried to make my entire presentation as interactive as possible without going too much into the mathematics behind them. A brief outline of the talk. I would begin by describing what is machine learning and its broad classifications. Then I would discuss some of the prerequisites that is needed to understand reinforcement learning in depth, and that would include Markov decision processes. A detailed description of RL will follow next, and lastly, I would discuss offline RL and genetic algorithm that is used in RL. These two are the major research areas which I had selected in reinforcement learning. Of course, there are others, but these two are currently within my scope. Now, the world is filled with data, right? A lot of data. In fact, pictures, music, videos, words, spreadsheets, and whatnot. And with this growing abundance of data around us, abundance of data availability, it makes perfect sense to utilize the data, to make use of that data. This is where machine learning jumps in. And as we can see from the slide, machine learning is nothing but the study of computer algorithms that can improve automatically over time through experience and by the use of data. Simply put, in layman's terms, machine learning can be viewed as a tool that uses data to answer certain questions. Now, these pieces broadly outline the major two sides of machine learning. Both of them are equally important. Using data is what we refer to as training, while answering questions is referred to as making predictions or inference. These things form the basic framework of machine learning, and let's see it together in brief. Now, training refers to using our data to inform the creation of a predictive model and fine-tuning of that predictive model. Now, this particular predictive model after training can be used to serve predictions on previously unseen data and answer certain questions. Now, as more data is gathered, the model improves over time. Now, machine learning, the traditional machine learning approaches are mainly divided into three broad categories, depending on the nature of the feedback available to the learning system. Now, the first one is unsupervised learning. I'm so sorry. The first one is supervised learning. The second one being unsupervised learning, and lastly, reinforcement learning. Now, subject of this talk centers around RL, reinforcement learning, which also happens to be my area of expertise. So before going into the details of reinforcement learning, let us just look at the other two techniques briefly. First, we will see about supervised learning. Now, as the name suggests, supervised learning happens under a supervision. The machine is presented with a set of labeled data given by a so-called supervisor, and the goal is to learn a general rule, a general function, or a mapping that maps inputs to outputs. Now, let us understand this with the help of an example. Suppose we have a data set of different types of shapes, which include square, rectangles, triangles, and polygon. Now, the very first step is that we need to train the model for each shape. If the given shape has 4 sides and all the sides are equal, then it will be labeled as a square. If the given shape has 3 sides, then it will be labeled as a triangle. If the given shape has 6 equal sides, then it will be labeled as a hexagon. Now, after training, what happens is we test our model. We test our model using the test set, and the task of the model is to identify the particular shape. The machine is already trained on all types of shapes. Right? The machine is already trained on all types of shapes. And when it finds a new shape, when it detects a new shape on the test data set, which it has not previously seen, it classifies the shape on the basis of the number of sides. And when it finds a new shape, it predicts the output based on the classification. Now, problems in supervised learning are mainly of two types: classification and regression. The shape predicting example which we saw just now is basically a classification problem. There are many supervised learning algorithms actually for solving classification and regression problems as well. But the goal of the talk is reinforcement learning, so I won't cover those. Now let's see about unsupervised learning. It is quite evident from the name itself that in unsupervised learning, models are not supervised using data labels. Instead, models itself find the hidden patterns and insights from the given data. Suppose the unsupervised learning algorithm is given an input dataset containing images of different types of cats and dogs. The algorithm is never trained upon the given dataset, which means it does not have any idea about the features of the dataset. Now, the task of the unsupervised learning algorithm is to identify the image features on their own. The algorithm will perform this task by clustering the image dataset into the groups according to the similarities between images. The unsupervised learning algorithm can further be categorized into two types of problems: clustering and association. An example of clustering we saw just now. An association is used for finding the relationships between variables in a large data set or a large database. It basically determines the set of items that occur together in the data set. Now, before moving on to the details of reinforcement learning, let us discuss the need for it. We want AI to be good at multiple tasks, right? And not just some selected set of tasks like classification, regression, clustering, and so on. Therefore, we want AI to generalize. But the question is, why is RL needed specifically? I mean, supervised learning and unsupervised learning are already present. So why do we need reinforcement learning? The answer is, there are certain tasks, to be honest, many tasks actually, where supervised learning and unsupervised learning fail. And when supervised or unsupervised approaches fail, RL comes to the rescue. Now let us understand this with the help of an example. Suppose a kid is learning to cycle and his father is assisting him in the process. The kid makes numerous attempts but fails to achieve the required balance and his father is holding him, right? Why does the kid fall? It is essentially because his brain and body is not coordinating. His body and brain simply doesn't know how to respond together during such an activity, right? But with repeated trial and failures, the kid finally manages to drive on his own. So this is how he learns to cycle through a trial and error process. Now suppose that the father decides to be smart and tells the kid, hey, listen, if you are able to drive straight, if you are able to drive straight for at least, say, 15 seconds, then I will reward you with a chocolate or something of his choice. But if you fall down before, you get nothing. Now, the kid will surely try to drive better than before because the idea of getting a reward is motivating him. In other words, he's being provided with a positive reinforcement. Now, as the kid keeps on driving straight for a longer duration, he looks forward to getting more and more chocolates. Technically speaking, he's trying to maximize his rewards over time. This particular idea is in the heart of reinforcement learning. This is the crux of reinforcement learning. And this is the very reason why reinforcement learning is named so. But how does supervised and unsupervised learning fail here in this particular example? Now, just imagine, if it was supervised learning, the kid's father would have said to him something like this: get on the cycle first, push your right foot on the pedal with 3 pascals of pressure, move your center of gravity 45 degrees to the left, and so on. Just putting in all the gory details of physics. Now, if the supervision was given to the kid at this scale, he would have probably never learned to cycle. This is the problem. So this is not supervised learning. Now, what about unsupervised approach? If it was truly unsupervised learning, the kid should have watched hundreds of videos of people cycling, figure out what is the pattern, get on the cycle to just reproduce it straight away. So neither supervised nor unsupervised learning helps. Now, there are several tasks like cycling where these approaches fail, and RL basically comes to the rescue. This reward-driven way of learning mimics the fundamental way in which we humans learn. For instance, the kid learns to cycle by intuitively training his body to not to fall down over repeated trials, right? So this not to fall down somehow is the key. The behavior of not falling down is captured by him through reinforcement learning. Now, owing to this property, RL is mainly used in tasks where the goal is to achieve near optimal control skills and efficient decision making. Now, let's see some mathematics behind RL. Firstly, let us view Markov decision processes, as this is the key to understanding reinforcement learning. Markov decision processes are often abbreviated as MDPs, and MDPs are nothing but a discrete time stochastic control process. It basically provides a mathematical framework for modeling decision making in, suppose, situations where outcomes are partly random and partly under the control of a decision maker. Now, example of a simple MDP is given in the figure. It has 3 states marked in green circles, 2 actions marked in orange circles, and 2 rewards shown with the help of orange arrows. Now, mathematically, an MDP is defined by the four-tuple definition, SAPR, where S and A represent finite state and action spaces, P represents the transition probability from one state to the other, and R is nothing but the reward function, which assigns the amount of reward obtained by an agent if that agent in a particular state, if it plays an action, the amount of reward obtained by that agent is given by the specific reward function, and it changes from environment to environment. Now here comes a crucial point. What is the goal in an MDP? The goal in an MDP is to find a good policy pie for the decision maker. The policy pie is nothing but a probability distribution over actions given the states. That's why it is written as pi A given S. So probability distribution over actions given the states are already visited. So in other words, pi mentions the action pi of S that is selected by the decision maker when he or she is in state S. Now, once an MDP is combined with a policy in this way, this basically fixes the action for each state, and the resulting combination behaves like a Markov chain. Now, this is because of two reasons. Firstly, the action chosen in state S is completely determined by pi of S, right? And secondly, the probability of being in state S dashed, demonstrated by this equation, at time instant t plus 1 is no more dependent on AT, but becomes entirely dependent on the state S itself, at which the system was in at time instant t. This is the key here. This is the Markov property. Now, the main idea behind RL is to learn from failures, right? Learn from errors, trial and error methods. It involves the agent environment paradigm. For example, we have a maze here, which will act as an environment, and a robot here, which we can consider as an agent. Now, task of the robot is to solve the maze. The robot performs some action in the environment, and as a result, the state in which it was in will obviously change. Now, the agent receives a reward for playing an action in the environment and tries to learn a policy by maximizing the expected sum of rewards. Now, mathematically, in reinforcement learning, the current state of a dynamical system is described by this four-tuple definition. Now, alternatively put, each transition of the agent from one state to the other is described by this very four-tuple definition. Let us see how. Now, small s is the present state of the agent, right? And small a is the action taken by that agent in state S. S dashed is nothing but the new state reached when the agent had played the action A in state S, and R is the reward obtained by taking the action A in state S. Now, there is sometimes an experience replay memory, which is also known as the replay buffer. Now, its purpose is nothing but to store the sequence of transitions, right? To store the sequence of S, A, S dash R's in the form of actually a sequence is stored in the memory, and the memory it's generally implemented with a circular queue, I think. And the purpose of it is to provide a memory to the agent so that the agent remembers its previous transitions, what mistakes or what good actions did it take earlier once it encounters a new state or a new situation. Now, the final goal in a reinforcement learning problem is to basically learn a policy, right? Which we already defined earlier. Now, policy is nothing but a distribution over actions conditioned on states, pi of ATST, right? In other words, any RL problem can be defined as a policy search in an MDP. So let us define a trajectory here. The trajectory is a sequence of states and actions of length, say capital H, given by tau, where H may be infinite. Now, for a given MDP M and a policy pi, the trajectory distribution P pi is given by this expression, where T0 of S0 is the initial state distribution, and T defines a conditional probability distribution that is used to describe the dynamics of the system. Now, This is really an important equation. The reinforcement learning objective J pi can then be written as an expectation under this specific trajectory distribution, and we are calling it as equation 1. Basically, what this equation means is that we are trying to maximize the sum of expected rewards accumulated over time. Now here, gamma is the discount factor that tells us how important future rewards are to the current state. A reward R that occurs t steps in the future from the current state S is multiplied by, say, gamma to the power t to describe its importance to the current state. This is the importance of gamma, and it's obviously a scalar lying between 0 and 1. Now that we are done with the basics of RL, it's time to have a look at the, say, one of the major research areas in this field, and that is offline RL. Now, reinforcement. Okay. Okay. No, just fire away, no problem. Hmm. Okay, so basically, the answer to the question is RL is not developed to replace supervised learning. It was developed keeping in mind to achieve superiority in those tasks where supervised or unsupervised learning approaches fail. For example, the cycling example which I already demonstrated, and there are tasks in which RL also fails. And the goal of this talk is to precisely cover some of those tasks where RL fails too. So you see, this replacement theory doesn't work, right? And as we go forward to discuss more about offline RL and the other research topic also, we will see that how the research gaps or the flaws in RL has been addressed specifically or is going to be addressed if an extensive research takes place. So that is my answer to the question. Was that satisfactory? Hello? Okay, great. Okay, so now moving on, reinforcement learning, as we just saw now, has been successful in mainly closed world, relatively narrow domains, particularly decision making, control, and manipulation tasks, right? While supervised learning, on the other hand, has proven to be effective in more open world and realistic settings. Now, if we look close enough, if we look closely, we can realize that there is an enormous gulf between the success domains of supervised learning and reinforcement learning. Offline RL is an attempt to specifically bridge this gap. This is what I was talking about. Now let's see, why do we need to bridge this gap? In other words, why do we need offline RL, right? Now offline RL has been developed to combat those scenarios where it is not feasible for an RL agent to directly interact with the environment or to have any interaction with the environment at all. Now consider a case where a doctor is trying to find the right type of drug to administer to a patient for treating a disease that he or she has, right? So if the doctor has no prior experience in dealing with the disease before, it would be absolutely impractical to employ a trial and error approach, right? I mean, he cannot simply keep on trying various drugs on the patient. That would lead to disastrous consequences. It might even kill the patient. Now consider another case where we want to build a self-driving car that runs between several cities. Say Kolkata, Delhi, Bangalore, and something else. Now we cannot simply expect to collect experience in the form of RL tuples like the one showed before, S, A, S dash, and R, by repeatedly visiting cities after cities, right? The thought of going from one city to another simply sounds pathetic just to collect data. It would be very costly and time consuming as well. Now, this is where offline RL comes into picture. So basically, offline RL is a promising area of research that aims to combine the control flexibility of RL with the data-driven success of supervised learning. Now, conventional classic online reinforcement learning, as we can see here, and which we also saw earlier, operates in a setting where we have a policy that interacts with the environment to collect data during multiple rollouts, right? So it uses the data to update the policy and then collects new data. Now, this term is important, of policy reinforcement learning. The term of policy RL is typically used to refer to algorithms that can utilize data collected by other policies. However, one thing is important to note, these algorithms still operate in a regime where they will collect data additionally as they proceed, right? So perhaps we have a policy that interacts with the world, collects some number of rollouts, adds those to a buffer, and uses all of the data from the buffer to update the policy. Now, the term offline RL refers to the setting where new data is not added. So online data collection is absolutely prohibited. We have a fixed data set collected by some behavioral policy, say pi beta, as we can also see in the figure right here. Typically, this behavioral policy would not be known and could not even be a non-RL policy. For instance, data generated by humans or carefully hand-engineered data, right? It goes into a data set D, which is used to learn a policy, and this policy is trained without any deployment. So this was all about the basic framework of offline RL. Now, if we could really design such offline reinforcement learning algorithms, then we could envision a new class of RL techniques altogether, right? When instead of having this active data collection system, we would instead have a setting where maybe our agent has collected a wealth of past experience from its variety of previous tasks, or perhaps from data that was given to it by humans, right? That data would then be used to train a model or value function or policy, typical RL terminology, to perform some desired tasks. And potentially, this process could be improved with additional data sometimes, but not always. So if we are really successful in developing offline RL algorithms, not only will it allow RL to generalize more widely, but also to apply it in certain domains where it is currently considered infeasible. For instance, just as I mentioned, healthcare, self-driving cars, stock market prediction, and large-scale real-world automation. That was all about offline RL. And let us now move on to the second major research area in reinforcement learning, which I had selected for this talk. Now, there is a big problem with RL. Agents trained using RL algorithms take a lot of time. Speaking from personal experience, believe me, even if RL algorithms are run on super fast machines like GPU, there are algorithms which could take days to run. So RL is basically slow. In other words, reinforcement learning is actually slow. But what is the reason behind it? The reason reinforcement learning is slow is because gradients are almost non-existent and therefore not very useful. Now, what does gradient do in supervised learning, right? What does gradient do in supervised learning? Suppose we have an image classification task, right? So in tasks such as image classification, gradients help by giving useful information on how parameters, that is, say, the weights and biases of the neural network, should be changed for better accuracy, for the better performance next time. Now, after every mini batch of training, backpropagation, which is a popular neural network learning algorithm, provides a clear gradient or direction for each of the parameters in the network. Now, however, in reinforcement learning, the gradient information only comes occasionally whenever environment gives a reward. Most of the time, our agent is taking actions not knowing whether they were useful or not. This specific lack of gradient information makes our error landscape look like this. I know it looks funny, but the surface of cheese represents parameters of our agent's network where no matter what the agent does, environment gives no reward and hence there is no gradient. Now, since there is zero reward signal, we don't know in which direction to change the parameters for a better performance next time. This is a big problem. Now, the few holes on the surface, on the cheesy surface, actually represent high reward corresponding to those parameters of the agent's network that perform well. Now, RL is sometimes inefficient because it doesn't tell the agent what it is supposed to do. The agent, not knowing what to do, starts doing absolutely random things, and only occasionally environment gives out a reward, and now an agent must figure out which of the thousands of action it took led to the environment giving that reward. That is not how humans essentially learn. We are told what needs to be done, we develop skills, and rewards play a relatively minor role in our learning. So this is a big problem with RL. So how to combat this problem? So as I was exploring alternatives to, say, gradient-based approaches to RL, I came across a paper titled Deep Neuroevolution. Genetic algorithms are a competitive alternative for training deep neural networks for reinforcement learning. Now, this paper combined reinforcement learning with evolutionary computing. Strictly speaking, the authors didn't even have to implement a genetic algorithm. As hinted above, this very same paper found that even completely random searches were able to discover good agents. Now, this means that even if you keep randomly generating agents, eventually you will find an agent that performs well and sometimes even faster than traditional policy gradient approaches followed in RL, right? This sounds insane, but this basically just illustrates our original point that RL is fundamentally flawed, as it has very little information for us to use for training an algorithm. But now the question is, how do we use a genetic algorithm approach in evolving RL agents? Let's have a look. Now, we all know that genetic algorithms follow Darwin's theory of survival of the fittest, right? They are commonly used to generate high-quality solutions to optimize and search problems by relying on, say, biologically inspired operators such as mutation, crossover, and selection. Okay, but what about RL's perspective on all of these things? Firstly, just imagine the agent to be an organism, any biological organism. Its parameters will be its genes that specify its behavior, which is nothing but the policy of the agent itself. Rewards will indicate the organism's fitness, that is, higher the rewards, higher the likelihood of survival. Now, in the first iteration, you start with X number of agents, say, with randomly initialized parameters. Some of them, pure by chance, will perform better than the others. Just randomly, pure by chance. And just like the natural evolution in the real world, we implement survival of the fittest. So what do? We simply take the fittest 10% of the agents and replicate them until you have X agents again for the next iteration. Kill the remaining weakest 90% of the population. Now, during replication of the top 10% fittest agents in the earlier step, we add a tiny random Gaussian noise to its parameters so that in the next iteration, you actually get to explore the whole neighborhood around the parameters of the best agents. So in other words, it basically provides variation in the genes or in the performance of the agent or in the exploration and exploitation balance achieved by the agent. Now simply keep the top performing agent as it is, that is without adding any Gaussian noise, so that we always tend to preserve the best of the best solution, just like as an insurance against Gaussian noise that might cause a probable reduction in the performance. Repeat the steps up to convergence and return the best agent as the solution. So this was simply one of the numerous ways that an evolution strategy such as a genetic algorithm can be used in combination with RL just to combat the fundamental flaw which RL has. Now, this particular field of research is equally deep and wide as offline RL. To conclude, I would like to say that integrating other learning techniques with RL carries a great potential. It is simply one of the best available methods that could take us one step closer to general artificial intelligence. right? So having said this, I would like to put an end to my presentation here. And the things that I covered today was just a drop of the ocean. A single talk is not enough to cover those in details, but I hope I was able to present an overview. I would also like to thank you all for putting up with me and being such patient listeners. And I would heartily welcome anyone who is interested to take a plunge in the ocean, or in other words, who is interested to work with me in these areas. Thank you. Okay, so any more questions do they have? Okay. Okay, so I'm just stopping to share my screen. Okay. Okay. Sorry, please come again. It obviously does. And this is the point which I precisely covered. So when you actually integrate an evolutionary strategy, say for a genetic algorithm, the particular example which I showed, when you do such things, what you do is you actually you actually deal with the fundamental flaw of RL, which is the absence of gradients, or I mean the less availability of gradients. You keep on iterating, you keep on uh, producing best solutions over and over again, and this is how genetic algorithm or any evolution strategy works in combination with RL. So this was the whole point. So yes, the answer to the question is yes, it definitely helps RL to get smarter, right? Just a step ahead towards general AI. Yeah, definitely. I would love to collaborate with some people. A specific amount of data will always be needed. So I think this notion of reduction should be a bit more specific. So it's kind of sounding vague to me at the present moment. So if the person, whoever asked this question, could be more specific about this notion of reducing training data, I could make an attempt to answer the question. Well, to be honest, I've never heard of such things because this is the first time I'm hearing this term, high dimensional interference problems. So if the person could actually specify what it is, then maybe I could answer what it is actually. Basically, I have never come across such things in the RL literature. There is obviously causality, While developing offline RL algorithms, causality is a big challenge. So the statistics people will definitely know what is causality, the science of studying cause and effect. So that is a challenge, but I'm not sure about this high dimensional interference. Yes, now I fully understood the question. Yes, it is possible. So if an RL system is able to learn from less training data in a better way than the existing RL algorithms, we will say that that particular RL algorithm, I mean the new RL algorithm, is more sample efficient, right? So I think he's referring to sample efficiency. So yes, that is possible. Okay, so goodbye till we meet again. Thank you, Shodayam. Okay, bye. So I'm disconnecting the meeting. Right.